Okay, so today we'll see what is in polarizing light, how that is also used to enhance the contrast of an image. A technique is called as polarization microscope. Okay, so before you go for polarization microscope, you should understand what is polarization. Okay, so we have come across the term polarization whenever there is a difference in the vibration front when it goes through some medium or it's by reflection. Okay. So what are the terms? So this is an example, a polarization that may happen because of a reflection. Okay. So this incident ray shows like vibration front on the plane of this screen, and a dark ring can be assumed to be vibrating perpendicular to your board. So it is vibrating, it goes and falls on a medium. Okay, so now we say it's unpolarized light because it is not discriminated, unpolarized light. Upon reflection, what is happening? On the reflection side, what do you find? Only one type of vibration is actually coming out. The refracted ray, it has the characteristic of both vibrating parallel to your screen and perpendicular to the screen. So this is unpolarized, this is polarized. The rays which are coming out, they are polarized. We say polarized, only one particular type of vibration front is allowed. Okay, so this vibration front, why it is allowed only in particular direction? It relates to the electrical field. So we say it is an electromagnetic wave. Visible light is electromagnetic wave. The electrical field vector actually interacts with the electrical field in the material. Okay, for a metal, do you have electrical field? There is no polarization. Two positive and negative are not isolated. There is no field. It's a bonding of metal ion and electron cloud. You cannot center the metal electron cloud at physical location and metal nucleus at some location. It's all same. When you have an ionic crystal, positive is somewhere, negative somewhere. Okay, so this will have a field now. Positive to negative, there will be a field. So this is called dipole. We said in the earlier class also, whenever the center of positive and center of negative charges does not superimpose one another, we say is non-centrosymmetry. Those type of material will have a field, and this electrical field when it goes on it, sometime it is opposing, sometime it will retard, sometime it will not allow it also. So this refractive medium on a certain inclination, not for all the inclination, only for certain angle, Brewster angle, we find the reflected rays is polarized and whatever goes through it is unpolarized. And similarly, as I told you, what the use of polarized glass. So on a road, we have unpolarized light entering on it. The reflecting one reaches your eye. So this polarized glass allow only this direction of light to enter your eye. The horizontal direction will be cut down. It will not be allowed to enter. So the very purpose of polarized glass is to cut down one direction, so that intensity, too much of intensity does not reach your eye. Okay. So the polarization may occur by reflection, Both the possibilities are there. The material is there. If it is reflected also, polarization may happen. In some case, when it refracting also, polarization may happen. So it all it depend on something called as the axis. Okay, on certain crystallographic plane, certain direction, we find a ray is just accelerated, some ray is decelerated. Okay, so as I told you, a plane polarized light everywhere it's same. That means if I draw a circle, all the vibration front will be fitting within a circle. On a cross-sectional view, if you see it, all vibration will fit within a circle. All the directions same. All the velocity and all the directions are same. Okay, when I send that unpolarized light through one medium, which is dielectric is assisting on certain direction, what will happen is like sometime what you find is like intensity your intensity of polarization takes place. Okay, so some direction we have some field, some direction we have some other field effect. Somewhere it is accelerated, somewhere it decelerated. So I have two characteristic of rays coming out when passes through one direction. So material which try to separate out the polarization light into two different varieties or two different paths, we call as bifurcent crystals. Okay. Naturally, a material may have one axis, and after reflection, ordinary ray which goes the same velocity goes in one direction, an extraordinary ray which goes faster compared to another ray or some vibration front, we call as an extraordinary ray. They go at a higher velocity. Okay, this will happen only it goes through certain axis. So this one, whatever is shown in the picture, this polaroid. A polarized sheet is nothing but it transmits the vibrating in one direction while absorbing those in the other plane. So such type of behavior is called a dichoric filters, a dichorism. Okay, one is filtered. So a polymeric chain, okay, within a polymer, when it is formed or stretched in certain direction, we'll find this kind of line type of arrangement. So schematically it shows like if an analyzer of this direction, okay, we send a polarized light, what will happen? 100% is going through across. If I send like this, what will happen? Will it go through this? Will not go through. If I send an inclination like these two, what will happen? Partially it goes. Or within this is the window, it can go like this, it can go like this. When it goes through the window, it can go near. Suppose I'm moving some cupboard, a bureau, inclined TV inside this door, the same manner. But anything on this side, if I do move it, only the width is possible. Okay. So such type of system, or we say it is analyzer. So I can put something on the path of an unpolarized light. What is coming out, it will be only plane polarized. Okay. Only this direction, this direction, this direction. Whatever that enters through this window, it is possible. Okay. So if I have another crystal, or if I say that with respect to this orientation, if I modify the orientation of analyzer, I rotate it now. Okay, it somewhere becomes nullified. Where it becomes nullified? This location. So here it is maximum. These are intermediate. This is 0. Okay, so the formula here says like a Moll's law. It says that intensity of light passed through analyzer depends upon intensity of the incident beam of lean polarized light. Okay, and the angle between the azimuth of polarization of incident light and transmitting axis of the analyzer. Okay, so so when you say this two, suppose theta, it is 0 means maximum. So aligned. So suppose the wavefront of vibration on the analyzer what you placed, they are at same direction. 0 is the difference means maximum light enters. Maximum light enters. Here 90 degree. No, nothing goes on. Okay. So that's what the relation of this angle. So if I use one analyzer, if I'm using analyzer, light is now going on this direction, enters. Okay. I use another analyzer which you call as an polarizer, or I suppose this is the door window. I just make a twist of it. Okay. So whatever rays goes to this direction, when I make it crisscrossed, 90-degree difference between the analyzer and polarizer, what will happen? That side, nothing is coming out. Okay. So if an analyzer and a polarizer, when you make a rotation, twice there is intensity changes. Okay, twice there is intensity changes. Suppose this is the polarized light enters your door, it goes on it. Okay, then I make this rotation, then I make this rotation. Okay, I make this rotation is possible. One half it is not there, another half it is there. Twice I have a maximum in the rotation, dichorism. our optic axis is 1. If I make a rotation like this, somewhere I get another intensity at some other angle, then we say the optic axis 2. So this is an polarized analyzer only 1. Okay, we have a maxima at one point, minima at other point. Directly you take an opposite side, it will be minimum. Directly opposite side will have another maximum. If I rotate it, okay. So such kind of system are used in polarization microscope. So polarization also exhibited a birefraction when it goes through certain material, and those material are mostly has some crystallographic orientation or allows electrical field are existing. So the dielectric constant of the material will affect the E vector of the light. Okay, electromagnetic wave is the electrical field vector, and if you have an dielectric constant for a material, surely these two will affect. Okay, so some of the system like quartz, calcite, rutile, tourmaline, others, okay, they are optically anisotropic and exhibit a property known as double refraction. Optical anisotropic means the property is not same in all the direction. Isotropy means same in all the direction. Okay, so certain crystal structures, the optic property is not same in all the direction. That is called as anisotropic crystals. Okay, so those anisotropic crystal will exhibit double refraction. Okay, what is double refraction? Okay, so when we say double refraction materials are bifurence material. Bifurence material split an incident ray into two components. Okay, and that traverse different paths to the crystal and emerges at two separate waves. Okay, so looking at this one, this is a material, bifurence crystal. So what do you see? A, B, C. This is the optic axis of the material. So only for certain direction of inclination, we have one type of vibration is going on some refracting path, another type of vibration going on some other refractive path. When a crystal is able to differentiate two vibrating front and two different paths, and is called as bifurence crystal. And that will not happen at any abrupt direction. It has to be at a particular inclination to the optic axis. This is the direction of optic axis. At certain inclination, if the light is sent, it itself divides into two light region. One is this path is ordinary rays, another path is another vibrating path. If it is perpendicular or parallel to the incoming light rays, what is happening here? The path is not modified, but there is something happening. What has happened here? Dot is not placed at this dash line. That means retarded. One vibration is getting retarded when it goes to a particular point. Okay. One vibration front is slow down. This vibration front is going without any disturbance. What is vibrating perpendicular to this screen? It is actually retarded. So this will go faster, this will come later. This will go faster, this will come later. So phase retardation may come into picture. Okay. Materials like calcite, quartz, molecularly ordered biological structure that contain single optic system are called as uniaxial system. So this system, only one axis we are referring, uniaxial system. Okay. So there are other class biaxial crystal with the two optic axis also exist, and so this is related to biological system which also acts like an polarizer analyzer inbuilt in the material itself. It will have an effect. Okay. So light by reflection get polarized, by refraction it also get polarized. When it get polarized, we say it follows two different paths. Okay, so the two different path. Okay, so what does that happen? What does that reason? Okay, so we say that the rays of light which goes through a crystal, which is taking two different paths, will be related by this expression. Bifurence refers to measurable quantity, a difference of refractive index for one set of rays, refractive index for another set of rays. What is refractive index? how refractive index and speed are related? Yeah. So C by N is your velocity. Based on your refractive index, the velocity is altered. Vacuum, water. Difference are there, then speed of light also will be altered. So now we are talking about crystal. In a crystal, in a particular direction, we say light is going in a faster manner. That is called as extraordinary rays. Light is going, continuing its same velocity, that is called as ordinary rays. So that's what actually represented by the two diagrams. Okay. So I can use this microscopes to identify refractive index of a material also. When you use this microscope, I have a crystal, I can find out what is the refractive index of the material. For our metallography application, material characterization, we are not into that type of study. But that type of study is used for the crystallography, geological, okay, who are working on minerals, okay, some minerals. You want to, geology people and all study a lot of minerals. A single crystal they prepare means they'll be studying a lot of things. So that kind of persons will be interested in estimating the refractive index. So you can find out what is the refractive index of a material. So what is governing? Okay, so what is governing for this different path is actually the dielectric constant of the material. On certain direction, it is allowing to go at the same speed. In certain direction, it is not allowing to go at the same speed. It goes faster. Okay, so this type of biference is nothing but after it goes through it, two different paths are going out. This biference can be a characteristic of a material by itself, or it is introduced in the material by external means. Intrinsic means by the characteristic of the chemical bonds within the material, like the calcite, tourmaline, they are intrinsic in nature. Biference or structural variance means they are created by extensive ordered arrangement of macromolecules or spacing. Okay, so because of some pull, some action or strain, okay, they become oriented in certain direction. The same thing also happen with the type of flow phenomenon or strain phenomenon or stress phenomenon. All this type of system may introduce two different rays to be developed. Intrinsic, okay, strained, stress, flow. Okay, you have seen any slide on photoelasticity? A transparent material will be there. They send light. Like tensile test to do it, you find that fringes, colors are appearing on the sample. Okay, transparent material, it is loaded. When it is getting strained, we find that the strain biference takes place. Physical location appears to be in certain colors, a stack of colors. Such kind of study is also carried out to study a 3D model. Okay, you want to experiment how the loading characteristics, how the stress are distributed. You do FE analysis. Experimentally, you want to study means you have to create a lot of strain gauges, try to measure it. One of the methods is called photoelasticity method. That depends upon strain biference. Forced alignment of molecules in a transparent solid deformed by externally applied load. Okay, a polyvinyl alcohol. Okay, so all these cases we say that there are two different wave fronts which are coming out different speed. Okay, now this is what we want to say. Along the optic axis, biferent crystal along certain optic axis. So one we say that a dot is going, another side we say that a horizontal is going along. So whenever the extraordinary refractive index is higher than the normal ordinary refractive index, what do you see in these two difference? Along the optic axis, actually it is going on the same speed of ordinary ray. But perpendicular to the optic axis, what is happening? This direction of vibration is not going in the same velocity because something is opposing it. So what is happening? The wavefront of this, it is major on one direction and it is lesser than the O in this direction. It is getting slowed down in particular direction. In this type of bifurant crystal, when ordinary refracting index is greater than the extraordinary ray greater than ordinary, what is happening? The same velocity with respect to optic acid, but the field is attracting the electrical field to go faster. Light is attracted. E vector is attracted by the dipole arrangement so that it goes faster. It goes faster, that is represented by this increase in width direction. Okay. So we have two profiles. One is the ordinary ray circle, extraordinary ray, which is like an ellipse. Say the velocity profile takes somewhat ellipse. The major axis is along the optics in both the cases. Okay, so when this kind of system is there, we call as negative bifurance. This type of system is the positive bifurance. So what is happening? It's all represented. All circles same velocity. This is what is expected. Circle. But when it goes through a crystal, the crystal, as I told you, it is affected. Velocity is affected by C by N. N is nothing but refractive index. Okay. And the refractive index is allowing the car velocity to go in optic as undisturbed, but it retards this direction. Okay, so what is happening now? Velocity of V3 is less. So fast axis, slow axis. Okay. So all this effect of the refractive index is indirectly related to what? What is this one? Dielectric constant. So metals, there is no dielectric constant. Only for ionic crystals, we say there is a dielectric constant. There should be some charge separation. Then we can spell dielectric constant. Okay, so I asked you whether any other polarization. We talked about only plane polarization. Any other polarization is there? Okay, so what is the polarization name? Circularly and elliptically polarized. Okay, circularly and elliptically polarized. Now, how do you get? This is a plane polarized light. Okay, plane polarized light. In particular, suppose this is the this E and O are represented as two different waves which goes to crystal. This is one. This is one. If I am putting a bifurant crystal and I am observing on my eye, object is there, I am observing on the other side. What will happen? These two rays actually merge and go to my eye. But they are traveling at different speed. There is a different, the phase angle between these two rays are modified. Okay. So ordinary ray, extraordinary rays, when you send through a material, it is responding in different velocity. So when it will happen, based on your material. So material has to respond to the light, respond to polarization light. We say a material optically isometric. Isotropic means it doesn't matter. Reflecting this side, no change. If I say anisotropic, my this side interaction will be different from this side interaction. So optical microscope, where Polaroid microscope, we find application for those material which are non-cubic. Non-cubic materials are anisotropic material. They are not isotropic material, optically anisotropic material. So which crystal system is not isometric? HCP, BCC, FCC. BCC, FCC mandal only A we write. Tetragonal HCP mandal we write CEA. So one of the axis, it is not symmetric. So they are not symmetric. They are non-symmetric crystals. So non-crystalline crystals will have a tendency to respond to polarization light. Otherwise, it will not respond to polarization light. So this polarization microscope actually it is used on this principle. Use light is falling on the sample, is reflected back. there is something change on polarization which we never accounted in bright field, dark field, phase contrast. Now, if you are able to discriminate or distinguish some of the polarization that may happen in your sample because of the reflection, then that will also enhance the contrast. That will not be revealed simply by our eye, because eye does not discriminate. Now the next thing, eye is not able to discriminate the phase, also the plane of polarization. If I'm looking at this tube light, means it is giving vibration all the front. If you just sitting aligning towards the tube light does not mean that only one type of polarization light enter my eye. So eye does not have a capability to identify the phase differences. It also does not have capability for identifying the polarization changes. Okay, by incorporating this analyzer, polarizer in the microscope, and if the material is responding to the polarization light, then it can reveal some of the features which is not seen in bright field, dark field, phase contrast. Additionally, you can see some features. So that is the idea for going for polarization microscope. Okay. So how this E and O, if they're differing by certain angle, we'll get circularly polarized light. If E and O differ by certain angle, we get elliptically polarized light. This elliptically polarized, it is inclined to right hand side. I can make it on the other side also. Just mirror it. Okay, it can also happen. But circle, nothing change. All the axis will be going to be same. So how this is possible? Okay, how this is possible? So usually from the object, if I place some polaroid, that is called as polarizer. Or from the image, light source is there. On the path, I put some this polarizing material. Then I say it is an polarizer. On the vision side, I put another same kind of material, that is a polarizer. We call it as an analyzer. Analyzer to eye, polarizer to the image, the eye, light source. Okay, so light from a polarizer light polarized light is made to go through the lens system from the light source, but only plane polarized going on it. Okay, so in the plane polarized light, after reflection or going through the material, it produces another wavelet, which is retarded one, E and O. We say E and O is separated out. That E and O, if you differentiate by 90 degrees, what will happen? So when it is different by 90 degree, what is happening? The resulting wave is, this is vertical. What has happened to this one? It's horizontal. Okay, this is vertical, and the resulting waves differ by wave path difference of 3 lambda by 8, lambda by 8, 5 lambda by 8, 7 lambda by 5. What is happening? Ellipsis occurring. If the path difference between E and O, okay, one plane polarized light you are sending on it, upon reflection, there is some change of light. Now these two lights both enter your analyzer or eye. Okay, so these two is going to always superimpose or interfere. We cannot avoid it. Okay, when it's superimposed, it may transform into a plane polarized to elliptical, circular, or elliptical. If I keep an analyzer on the path before your eye with this orientation, these two are called as crisscrossed. These two are called crisscrossed. 90 degrees it is rotated. Which will the maximum intensity that goes to the analyzer? It is represented by this amplitude. So this one goes the maximum. What about this one? 0. What about this? Okay, like a spring, you try to send it across and slot. Your circularly polarized, elliptically polarized can assume to be a spring, and there is a vertical slot. I can put the spring and I turn it, it will come to the other side. So on certain direction, partially some light will enter through the slots. So that's what we say as an elliptically polarized light. Intensity is not equivalent to this one, but it is reduced. Intensity of this one is not equal to this one or not equal to this one, but there is some difference in intensity. Now, similar phase contrast microscopy, if I put polarizer and analyzer in the image, the features correspond to this difference in O and E. Okay, will be revealed by intensity contrast of this magnitude. So, if a sample is supposed to have exhibit these characteristics, that can be utilized and be seen to see the features of the sample. Without analyzer polarizer, it is simply a bright field. If I use a polarizer and analyzer and the material is responding to your polarization light, if the material does not respond to polarization light, this sundial will not occur. There is no separate E and E. Okay. Any metal sample which is not responding to polarization light, if the vibration front is coming in this direction, it falls on the sample. After reflection, it will be turned like this. Any metal sample which is not responding to your polarization, what will happen? If it is vibrating on this direction, reflecting back will go in this direction. So I have placed polarizer and analyzer crisscross. Then what will happen now? What will happen? I'll get light because polarization is sent like this direction. Analyzer is vertically crisscrossed to the polarization direction. After falling, it is actually reflected back like this. Okay, when I get a crisscrossed, a bright light, your material is not responding to polarization light. That is the first step to know whether your material is responding to polarization. If a material is not responding to polarized light, there is no use of putting that material in polarization microscope. So whichever crystal system, metallic system which are non-cubic, which is having hexagonal HCP structures, non-cubic structures, tetragonal structures, only those material can be put in your microscope and see. Okay. Elliptical, circular, elliptical, this is plane polarized, elliptical, circular. So all this happens, the phase lag, E and O, they are differing by some phase lag. When it is multiple of lambda by 4, it is circular. Okay. When it is multiple of lambda by 8, then it is elliptical. And that elliptic axis also will be modified. So these things are used in polarization microscope. Okay. So what is polarization? Light I am trying to convey you. Okay. What is polarization means? It is a vibration front of light. If it is any light source will be unpolarized. It will vibrate in all the direction. If you want to put a particular polarization come into picture, I have to put some kind of a dichroid material or a polarized sheet. So only one type of polarization will come out. Or if I make to fall on water or refractive medium, at certain angle, I find reflected rays. Okay, this is what you see in the first one. By reflection also polarization is possible. And what is this? By refraction also a polarization possible. This difference in phenomenon in refraction correspond to material property. So a material is called bifurence when it has two paths. Okay, one optic axis. The material may also have multiple paths, multiple axes. So all the cases we have one rays which is going in different path, another rays goes in different path. So unpolarized light is now polarized into two different pathways, and the speed of that are varying. Okay, so in positive or negative bifurence material, So this is like positive. Ordinary refractive index greater than ordinary. Here, refractive index of extraordinary is less than ordinary. Okay. So when a material falls on this kind of material, there are two different waves, and these waves will superimpose again in your image plane, because anyway you put another lens and goes to your eye. Okay. So still we'll have details revealed by this kind of structures. Okay. If you are using this kind of material, what's the advantage? What's the advantage? Okay, anisotropic materials, the contrast can be enhanced by this phenomenon. Okay, later we will see that we can also able to look at color microstructures. Color is not characteristic of material, but I can produce some colors that is correspond to changes in the intensity, changes in the polarization in the material. Okay. Okay, so we'll see later how this microscopes appear. Okay, in general, the arrangement is shown here. No? Source, you put a polarizer. Through condenser, it goes to sample. From the sample, it goes to objective. Okay, this we'll see later, like compensator, retarding plates, and you have an analyzer. This is where the image is taking place. This is for transmission type of microscope. Okay, so the same thing is for your in case of metallography sample, what is that? Light source, polarizer. This is the mirror, object lens, again goes back. Now what do you find? The plane polarized light is vertical, here horizontally. Now it has changed this inclination and goes through your analyzer. Analyzer and polarizer is crisscross placed. So this is horizontal, this is this direction. Okay. So when a sample is changing, responding to the polarizing light, what is happening? The horizontal vibration is converted into this direction, but this will not go through your analyzer. So that means the material is responding. Okay, if it is not responding, what will happen? This one will be reflected in this direction, and that will goes to analyzer directly. So it is not optically active sample. Okay, so this is an example of polarization microscope. I will show the image and I will just stop here. Okay, so what's the beauty of this technique? Okay, so which type of crystal system? What is the alloy? Based on titanium. What is the crystal structure of this alloys under? Anisotropic. They are not cubic systems. Okay, so it is not BCC or FCC. It will have what structures? Non-cubic structure. Okay, so it will have SCP structures also there. Titanium alpha, beta, brass alpha, beta. All this corresponds to non-isotropic structures. So the grains, this grain, this grain, this grain, different grains are exhibited with different colors, because these grains are responding to the light in different form. So this grain, it have produced some ordinary ray or extraordinary ray with some phase angle. This would have produced some other phase angle. Okay, so color images is possible with the use of polarized microscope. And added advantage, so what is that added advantage? Now there are two images. Okay, left hand side, bright field illumination of a metal sample. What's the sample? Zirconium. Zirconium is what? What structure? It's not BCC, it's not FCC, it is HCP structure. Okay. So this is a bright field image. Grain boundaries are the grain is there. There is no discrimination on different grains, what type is not there. You observe the same now in a polarization microscope. Each grain will be behaving with the light in different form because it's an anisotropic characteristics. And it will produce different phase lag between E and O. Okay. Based on which index, so which is bright means in analyzer 100% is passing through. Somewhere it is gray, light gray. That means there may be elliptically, maybe 5 by lambda by 8, or 3 lambda by 8, or lambda by 8. So those goes partially in some direction. Dark color, they are 90-degree changes there. So it is not allowing light to go on the side. So same grain, I am now able to look at more clearly, distinguish them. Okay, so that is the nature of polarized microscope. It is not, it is beyond contrast. The contrast is one jump or two-fold jump. Okay, you will discriminate the grains by this kind of structure. So the advantage is only for active materials. You can find out different grains by different colors, grain orientations. Okay, so this is an applications related to optical microscopy. Okay. So sometime an isotropic material, if you make an oxidation, metal is made to oxidize. It form oxide film. But the oxide film thickness will not be same on different grains. That is different. Okay, in certain grains it will be thicker, certain grains will be less because of some diffusion differences on different planes. So now we have oxide is a transparent film. Okay, oxide film is transparent. So, but the oxide film is not of same thickness because the thickness is varying. The refractive also that will be modified. Okay, so we can use different thickness of oxide layer on different grains to produce your color metallography on the structures. Okay, so find further discussion on the microscope, polarization microscope, and the use of retarded plates, common center plates. We'll discuss in the next slide. Okay, next class we'll see about that. Okay, so this is the one variant. The other variant we have is differential interference contrast microscope. With that, the special type of microscopes will be over here. Okay. Any doubts? Hmm? Yes, sir.